What's up?
Hey Ryan, long time
It's
no
been a
see. Long time no
it's been a
see.
while.
I know. I had to
But
cancel my office hours last night because I had to catch up on a lot of work like that was due that night. Yes, last night.
it's so funny. I didn't even check the school thing. I thought I was like, oh shoot, I'm gonna have to miss a meeting.
Dang. Were you busy last night or
Yeah, I think I was busy because I like
Mhm.
just started summer school. And the thing
Oh.
is, the work is really easy. It's just that like I just have to do it, and like I can get it done in like a 6 week course in like 1 week.
6 week course done in 1 week? Oh, really? What the heck? Like, is it asynchronous or
Yeah, it's the
synchronous?
summer school computer technology.
Oh, summer school of computer technology. Oh my God. Wait, so like, is it like in person or online?
It's all online, but you have to be
Uh-huh.
in person to take tests. And then basically, some student asked, like, why do they need to be there in person if they could just take the test? And they said, like, that's how the school gets paid. So,
Oh, dang. I see how that works.
hmm
Dang. Hey, Zinyan, how are you?
Hi,
Yeah.
how are you guys?
Uh, doing fine, doing fine. I had to cancel my office hours last night because I had homework due and then I was rushing to finish it. I procrastinated too much.
Oh,
Yeah.
hmm
Mhm.
but now, like, it's just spreadsheets. So,
Spreadsheets for the homework.
yep.
Yeah. Let's see. Yeah, it's been a long day for me. I just got off a session. So now I'm just resting now. Yeah.
Do you guys, when do you got finals?
When do I have finals?
Yeah.
Um, I have finals next Wednesday. That's my only final. My only final is next Wednesday. But finals starts this Friday and then up until Thursday of next week.
Ooh.
Yeah.
So you're just resting. All right.
Yeah, I'm just resting right now. Yeah. But I get to have like answer questions, any questions that if you have any, Zinyan.
I was doing the worksheet
Yeah.
for workshop 15.
Uh-huh. I'll make you co-host, so maybe you could share the screen and then we could work through those problems together.
Oh, okay.
Uh-huh.
So I was just looking at your content review.
Mm-hmm.
Where is it? Yeah. So for this one, I was confused about the cyclohexanol and
Mm.
BF3.
Yeah, so that right there is gonna come from like cyclohexanol is a cyclohexane ring with an alcohol attached to one of the carbons of that cyclohexane ring, right? So um let me annotate that for you here really quick. Let me get my iPad and join this really quick. Okay. um, Okay, so cyclohexanol looks something like this, where we have a six-membered ring, and then on one of the carbons we have an alcohol, cyclohexanol, right? The BF3 is going to be something like this, where we have a boron attached to three fluorines like that, right? We know that this boron here only has six electrons because it has three bonds, um, meaning that it has an empty p orbital here, right? Boron is one of those weird atoms that even though it has like six electrons and three bonds, it will have a neutral charge. Um, it won't have a positive charge like a carbocation, right? Because if a carbon only has three bonds and missing a bond, it will have a positive charge. But the boron here is neutral with three bonds, right? Where the alcohol oxygen here is going to use one of its pairs of electrons to attack that empty p orbital that that boron has, right? When that happens, we're going to get this structure here where the alcohol oxygen is attached to that boron that's still attached to three fluorines, and then this oxygen here is still attached to a hydrogen right there. What charge will oxygen have with 3 bonds?
Positive.
Yeah, positive charge. What charge will boron have with 4 bonds now? This is a tricky one.
It's a negative.
Yeah, negative charge, right? So think of this here as a good leaving group. Like a bromine, chlorine, some good leaving group, OTS, OMS, OTF. And then we could just kick that good leaving group out like a Friedel-Crafts reaction, or SN1 reaction, or E1 reaction. When we kick that group out, we're gonna have a positive charge on that carbon right there that lost the bond, right? So that's the source of that right there, the carbocation on a cyclohexane ring there. So think of number 1 as this whole thing here, which came from that mechanism that we just did, right?
Is
And
does like the temperature matter,
um
or is it just
oh
there?
yeah, I think yeah, the temperature, like I think that's what they did in lab. Like that's the optimal conditions. You didn't learn about this in lecture, so I don't think you need to worry about like this thing here. But you did need to know like the positive charge here, because you know how we have a benzene ring here, and then we have an R group, which is an EDG, right? We know that R group EDG is an ortho para director, where if we locate the ortho and para carbons, which is going to be that carbon, or this carbon, we choose the position that has the least amount of steric hindrance, which is the para carbon, right? So that's para carbon here is going to be the nucleophile. The electrophile is going to be that positive charge carbon that we just created from the cyclohexane ring, right? Which this is going to be the star carbon right here, attacks the dot carbon to get that new bond between them like that.
Is this a kind of reaction we learned? Is this alkylation or no?
Yeah, it is like alkylation, but the electrophile here is just different. Like it's not technically Friedel-Crafts alkylation because we don't have any metal catalyst like AlCO3 or FeBr3 or something like that. It's just a carbocation electrophile. Like any strong electrophile will still work. Can still be attacked by a benzene ring, right? Like
Okay,
a carbocation can be attacked by a benzene ring, which we got the carbocation from that first step.
okay.
Uh-huh.
We just need to know that like when there's like an alcohol and a BF3, it just creates a cation.
Yeah, whenever there's an alcohol and a BF3, it creates a carbocation and where the alcohol is attached to. Yeah,
Okay.
it does not have to be an alcohol. It could be an amine as well, or a sulfur, right? Like any electronegative atom that has a pair of electrons, or any atom that has a pair of electrons, right? Like this oxygen here has 2 pairs of electrons, so that's why it was able to attack the boron and get that good leaving group, and then that good leaving group leaves to get the carbocation. It does not have to be oxygen, it could be NH2 as well, because that NH2 will also have a pair of electrons that can attack the boron,
Okay.
right? Yeah. Hey, Efrain, how are you?
Hello, I'm good. How are you?
I'm doing fine, doing fine. Do you have any questions so far on the thing? If not, you could just like listen in here.
I do have a question. It's about I was doing one of the practice problem sheets and I came across a problem where I was reacting a ketone with I think it was CH3ONA and CH3OH. And the answer was that there was no reaction, and I was just wondering how we got no reaction.
Off. Uh, wait, hold on. Could you hear me fine, or do I sound robotic?
It's a little laggy.
Let's see. Wait, let me turn off my camera really quick. Let's see. Okay, testing. Okay. Is it much better now? Like, am I still robotic?
No, you sound good.
Okay. That's good. Oh, could you repeat your question, please? You cut off at the beginning for me.
No, it's all good. I was doing one of the practice
Uh,
problems in one of the sheets from Maria, and I came across a problem.
mm-hmm.
I was reacting a ketone with CH3ONA and CH3OH, and the
Mm-hmm.
answer was that there was no reaction, and I was just wondering
Mm.
how we got no reaction from that.
Yeah. I'll make you co-host, and can you share your screen so I can just like see what is the specific reactant and reagent to see what's going on?
Yeah.
Uh, yeah.
Can you see my screen?
Yeah, I can see it. I can see it.
It was, hold on, let me find it. It was L.
Mhm. L. Okay. I see. Oh, okay. I see what's going on here. Um, when you see a strong base like RO minus or NaOH, right? Hydroxide ion, and with heat and a carbonyl, that's a big sign of aldol condensation or aldol dehydration, especially if you only have one carbonyl, which gives you a big sign of a self aldol
Oh, okay.
reaction, right? But what kind of carbonyl do we have here? An aldehyde or a ketone?
This is a ketone.
A ketone, right? And do you know what is more reactive, an aldehyde or a ketone? Like what has a bigger positive charge on the carbonyl carbon, an aldehyde carbonyl carbon or a ketone carbonyl carbon?
The aldehyde?
Yeah, the aldehyde carbonyl carbon has a bigger positive charge than the ketone carbonyl carbon, so that's
Mhm.
more reactive, right? If we make that enolate ion by deprotonating the alpha hydrogen, right, and it doesn't matter which one, we could get like multiple um enolates because we have like multiple alpha carbons. One could be that. Another option could be this right here. If we deprotonated the other alpha carbon, right? Our electrophile here is a ketone, which is not electrophilic enough for the enolate to attack. It has to be an electrophile from an aldehyde, right? So for aldol reactions, um, the electrophile that we attack with the enolate that we create at the beginning has to be an aldehyde.
Oh, okay.
Yeah. Unless it's an intramolecular type aldol, right? Where if you have something like this, right? Where we have two carbonyls in one
Hmm.
structure, we know that we want to create the most stable ring. So let's say that this star atom that I started here is going to be the nucleophile, one, and then this dot carbon here is the electrophile, two, three, four, five, to make a five-membered ring like that, right? This is able to be the electrophile, the ketone, even though it's a ketone, because this is going to be an intramolecular reaction. An intramolecular reaction makes things happen way faster,
Oh,
right? But in this case, we're trying to do an intermolecular reaction because the nucleophile is separate than the electrophile. If the nucleophile is on the same molecule as the electrophile, that
mhm.
will speed up everything. It will make this ketone be able to act as an electrophile for intramolecular aldol.
Okay. So it has to be an aldehyde.
Yeah, for the
Oh,
electrophile, right?
okay, that makes sense. And then I
Uh-huh.
had one more question.
Hmm.
Um, I kind of get confused, like where like where the nucleophile will attack the carbon. For example, sometimes I see that the carbon that's connected to the oxygen is attacked. Then I see that the alpha carbon is attacked, and then
Mm,
sometimes I see it's the beta one. So in what
mhm.
situations would we get
Right.
each?
So if you get this structure here, the only electrophilic carbon is this carbonyl carbon right here.
Mhm.
That's the only positive charge carbon. But if you get something like this, where there's an alkene right next to that carbonyl, an enone, there are two electrophilic positions. This position and this position as well. This beta position is electrophilic because let's draw in the resonance structure of this. When we draw in the resonance structure of that, we get this here. Where you notice how at the beta carbon, there is going to be a positive charge there. Right. Like, do you get how I got to that resonance structure there with the arrows that I drew?
Yeah.
Right. Where at the beta carbon, there is a full positive charge, making that beta carbon a stronger electrophile. Right. This beta carbon has a big partial positive charge. This carbon carbon here has a smaller partial positive charge because that carbon carbon there has no full positive charge on
Mhm.
the resonance structure. Right. So depending on what you use as the nucleophile, a hard nucleophile or a soft nucleophile, it will attack either the carbonyl carbon or the beta carbon.
Okay.
Right? A hard nucleophile will be able to attack the weak carbonyl carbon. Every other soft nucleophile, which is like the most common case that you see, will
Mhm.
attack the beta carbon of the enone. Right?
Okay.
So the hard nucleophiles you see are either an H minus source or an R minus source. And the H minus source that you'll see are lithium aluminum hydride or sodium borohydride or NaH. The R minus source that you'll see are RMGBr or RLI, Grignard or organolithium. These are your hard nucleophiles that would directly attack the carbonyl carbon. Right? Soft
Mhm.
nucleophiles in this chapter that you'll see are more like the enolates, the enamines. But the nucleophile here is not the oxygen or nitrogen. The nucleophile here is the alpha carbon of those enolates and enamines that attacks
Okay.
the beta carbon, right? Other
Mhm.
soft nucleophiles that you'll see are like OH minus, OR minus, CN minus, BR minus, every other nucleophile that you see in 118A for SN2 reactions, right?
Mhm.
Another thing is also a weak organometallic reagent, the Gilman reagent, the R2 copper lithium, R2CuLi, right? We only add one R group to the beta carbon. So this is a weak organometallic reagent, the R2CuLi, the Gilman reagent.
Okay.
Right? And then you might see that like if when you do reading or like watch videos as a 1-2 addition or 1-4 addition. That's because for the enone, we label that atom oxygen 1 and then 2 and then 3 and then 4. When the carbonyl carbon gets attacked, that's called a 1-2 addition. When the beta carbon gets attacked, that's called a 1-4 addition.
Okay.
Right? Hard nucleophiles do 1-2 addition or attack the carbonyl carbon.
Mhm.
Soft nucleophiles do the 1-4 addition or attack the beta carbon.
Okay.
Uh-huh. Of the enone, or you might see it as alpha, beta, unsaturated, aldehyde or ketone or carbonyl, right? Because there is an unsaturation between the alpha and beta carbon,
Mhm.
like a double bond there. A short way to saying enone. Alkene next to a ketone. It could be an aldehyde though.
Okay.
Uh-huh. Yeah.
And then when would the alpha carbon attack?
Oh, you mean the alpha carbon like be attacked?
I
Oh,
think I've seen some instances where the alpha carbon, I
mhm.
think that's the nucleophile.
Right. So the alpha carbon will attack whenever we have an enolate ion. So let's say we have something like this, where this is the alpha carbon right here. That alpha carbon will attack if it gets deprotonated by a strong base, like OH minus, right?
Okay.
Because when we deprotonate that, that's going to give that carbon a negative charge, like that. And that's when it attacks. It doesn't have to be an enolate ion. It could come from an enamine. Like let's say we have this enamine here. When we draw out its resonance structure, this is what it looks like. Where what charge will that alpha carbon have, do you predict when I finish this resonance structure?
Negative.
Yeah, which is why that alpha carbon there is nucleophilic, because it has that negative charge there.
Okay.
Mhm.
All
And
right.
that's the alpha carbon that would attack the beta carbon of the enone, or 1,4 addition. That's a soft nucleophile.
Okay.
Uh-huh.
All
Yep.
right. Sounds good. Thank you. That was like my big confusion.
Yeah, no problem. Like as we work through those problems, just keep that in mind. I hope that helps.
Thank you. Thank
hmm
you.
Yeah, no problem.
Wait,
Any, uh-huh.
quick question.
Yeah.
Like when do you consider is an Aldol condensation?
Mm. It's gonna be an Aldol condensation if your nucleophile is an enolate, like that alpha carbon that we just talked about, the alpha carbon of an carbonyl, right? Like a ketone or aldehyde. That's always the nucleophile, the alpha carbon of the enolate, right? The electrophile for aldol condensation is always the carbonyl carbon of an aldehyde or ketone. So let me share my screen to show what that means. Right? Aldol condensation versus aldol dehydration. Right? Condensation will have no heat on the reagent. Dehydration will have heat on the reagent. And you will most likely go through the dehydration route because there's like in most practices, there's heat there. Um, the nucleophile for aldol reaction is always the alpha carbon of an enolate, right? Or the ketone or aldehyde, right? The electrophile is always going to be a carbonyl carbon of aldehyde or ketone, right? Most likely aldehyde, right? It would be ketone if it's intermolecular, like we talked about earlier for the electrophile. If it's an intermolecular aldol, then the ketone could be your electrophile. But if it's intermolecular, your electrophile would be aldehyde. The product that you're going to get is either going to be an aldol from condensation with no heat or an enone from dehydration with heat, right? So let's look at an example. There are three types of aldol as well. There's self-aldol versus mixed aldol versus intramolecular aldol. But it all follows the same nucleophile electrophile thing. Nucleophile is always the alpha carbon of the enolate. Electrophile is always the carbonyl carbon of the aldehyde or a ketone. So let's look at this example here, where all of these, right, happen in basic conditions, right? Always basic conditions. The reason why we always need basic conditions is because we want to form the enolate ion, right? We want the negative charge on that alpha carbon right there. To get that negative charge there, we have to deprotonate it. And to deprotonate it, we need a strong base like that, right? Which is going to give that alpha carbon a negative charge right there. That's the nucleophile that we want for the aldol. This is going to be self-aldol, where I'm going to bring in another version of the aldehyde right there, where this carbonyl carbon is the electrophile, nucleophile attack electrophile, pop that up there. And then we get this new bond between the star and the dot atom right here, right? Where that's the new bond between them. And then that dot bond is attached to a methyl group, which is this methyl group here. And it was attached to a double bond O, but we popped that double bond O into a single bond O minus, like that, right? The next step here is to protonate that O minus using water that we formed earlier here. water gets formed when this hydroxide ion grabs the H, right? So let's grab that, kick that out, and then get this aldol here. This is an aldol because we have an alcohol beta to an aldehyde, aldol. It does have to be an aldehyde. It could be a ketone as well, but this is just what an aldol is. When you have a alcohol beta to the carbonyl. We don't stop here because let's say we have heat, right? Which you will most likely have on the arrow. If you have heat, you keep going further, where you're gonna get rid of that alcohol, dehydrate the alcohol, and put a double bond between the alpha and beta carbon like that to get your enone like that, right? And here's the whole mechanism on how to do that, right? So let's bring in another strong base to deprotonate that alpha hydrogen right there. That strong base right there is going to do that, generate the enolate ion again. Right. You might see the enolate ion, like the arrows for that, be like this instead, like deprotonate that, make a double bond there, and then pop the double bond into the oxygen, which is the more common way. The reason why they do that is because this is the more major resonance structure right here. But the nucleophile here is not the oxygen minus. The nucleophile is the carbon, because the carbon with the negative charge is less stable, right? But the nucleophile here is that carbon right there. And then this is the last step here, where we're gonna reform that carbonyl, carbon double bond oxygen, shift the double bond to that carbon right there, the bond right there, and kick out the leaving group OH, right? We're gonna make a double bond between the alpha and beta carbon. And then we always said that this OH was a bad leaving group, right? But this bad leaving group is able to leave because of heat that we added and basic conditions. There are other bases around to support that, like a lot of OH minuses around to support that OH minus leaving, right? And that will give us the final product here, this enone right there, right? As we reform that carbonyl, shift the double bond between the alpha and beta carbon, where that's the alpha beta unsaturated and saturation, and then the methyl group's there. So this is the aldol dehydration enone product. So that was self.
The aldol condensation always results in an enone.
Aldol dehydration always results in
Dehydration,
enone. Dehydration. Aldol condensation will result in an aldol,
okay.
right? But you'll most likely go to dehydration.
Okay. I had a question for the first step. I think do you remember like talking about Geminal Diol?
Oh yeah, the Geminal Diol hydrate reaction thing.
Yeah, like
Yeah,
when the negative OH attacks the carbonyl instead
right.
of the hydrogen.
Instead of
I'm
hydrogen.
confused how to like know to differentiate them.
So that does happen as well to create that O minus and then OH there and then H, OH. And then that gets protonated to get the geminal diol, or what Pascal calls it, a hydrate, where there are two alcohols on the same carbon, right? This hydrate here, or geminal diol, this is a conceptual thing as well, which could show up on the exam, is very unstable. It does not exist very long, cannot be isolated, cannot be maintained in a long time. Like it goes away quickly. Right. So this can happen in the solution as well, but it automatically goes backwards to this form here, right? So let me make the arrows clear. It will favor that form over this unstable geminal diol here, right? Where this enolate ion here is relatively stable, which can exist for a long time. Right. So this is more for conceptual question.
Is that because it's like we prefer to attack the well, is it related to like the alpha beta position, or I don't know.
Oh, so another way you can think about it is that acid-base reactions and intramolecular reactions are the fastest reactions in OChem. Right, they happen before like nucleophile attack electrophile. right? Also another thing is that you notice how we use base here. This strong base will look for the most acidic hydrogen because we said that acid-base reactions are fast, right? This is not an acid-base reaction. This is a nucleophile attack electrophile reaction. For an acid-base reaction to happen, the most acidic hydrogen is the alpha hydrogen here. This is the most acidic hydrogen, right? Because the conjugate base that it forms is stable with resonance, right? Stable conjugate base, acidic hydrogen there. If you have something like this, instead of basic conditions, you had acidic conditions, H2SO4, water, right? Then you could get more of the diol, Geminal diol here, hydrate, right? Because we can never deprotonate this alpha hydrogen anymore, right? Because we are not in basic conditions anymore. We're in acidic conditions, where the first step is to activate the carbonyl by protonating it, and then the water can attack to get this Geminal diol. But if we're in basic conditions, we look for the most acidic hydrogen, which is this alpha hydrogen here.
Okay, that makes sense.
Yeah. So in acidic conditions, look for the most basic oxygen, no, basic atom, which in this case is the oxygen here, right? To protonate and activate the carbonyl, where the water can then attack after it gets protonated and activated. In basic conditions, you have to look for the most acidic hydrogen, which is the alpha hydrogen here, rather than attacking the carbonyl carbon, because that's going to happen slower than the acid-base reaction here. Right. And the nucleophile for Aldol, Michael, and Robinson are all enolate ions. They all happen in basic conditions, right? Chapter 18, think of that as in basic conditions. Chapter 17, think of that as in acidic conditions, like creating the acetal, hemiacetal, hydrate, geminal diol, imine, enamine. All of those things happen in acidic conditions. But for chapter 18, when we talk about Aldol, Michael, Robinson, alpha alkylation, and stuff like that, all of them happen in basic conditions.
Okay. Oh, and I had another question on the worksheet.
Yeah, let me stop sharing my iPad and share your.
Yeah, I don't know if you went over this, but
Oh yeah. So this one here, I didn't go over. But we could walk through this here.
okay.
Um, what do you think the first reaction would do?
Um, make carbonyls from the alcohols.
Right, carbonyls from the alcohols. That's the first step. Now, what do you think the second step is gonna do?
The carbonyls come. I don't know what the reaction is called, but they get protected with the 2O.
Yeah, cyclic acetal.
Okay.
Right, protected. Right, protecting group. Nice. The third step.
Um, it breaks like ozonolysis breaks the double bond. Yeah.
In half and put oxygens like that. Right. So now I'm gonna draw out the hydrogen here to show that, that's an aldehyde right there. The third and fourth step are ozonolysis. They go together. Now, the fifth step, 1EQ of the thioacetal protecting group will react with the more reactive functional group. What is more reactive, an ketone or an aldehyde?
Aldehyde.
Yep, an aldehyde. Where that aldehyde there will get protected by the thioacetal. Right. Now, once we do that, we got the next two steps, which is reduction, right? And that's just going to reduce the I'm just gonna do it at this part. Reduce this carbonyl here, the only carbonyl that's open, into the alcohol, right? And the acid, water, and heat, right? That would also do something else as well. That would deprotect the cyclic acetals with the oxygens back into the carbonyl. That's the deprotecting step. The acid, water, and heat, right? It doesn't deprotect the thioacetal because that's not the deprotecting reagent for that. The deprotecting reagent for the thioacetal, to go back to the carbonyl, is that chemical soup right there, the mercury calcium thing, right? Which will convert this back into the carbonyl. Final answer, right? Where we could re-straighten this to make it more clear by saying this is 1, 2, 3, 4, 5, 6, 7. Longest chain is 7. Where the first carbon is aldehyde. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. At carbon 2, there's a carbonyl. At carbon 5, there's a carbonyl. At carbon 6, there's an alcohol. Right.
So the reducing agent just get rid of the cyclic acetal.
Oh, right. So the reducing agent here does not get rid of the cyclic acetal to the carbonyl. That reduces the only open carbonyl, C11O, into a alcohol. The thing that gets the cyclic acetal back into the carbonyl is the acid, water, and heat. This converts cyclic acetal back to carbonyl, right? The acid, water, and heat. That's the step that goes back to the carbonyl, the acid, water, and heat.
Okay. Makes sense. Thank you.
Yeah, no problem. Mhm. Where the reducing agent only reacts with the open carbonyl. And then we protected every single other carbonyl. The only open carbonyl was on carbon 6, which is why carbon 6 there's an alcohol there now. Because we reduced that carbonyl to the alcohol using the sixth step. And then the seventh step converts the cyclic acetals on carbons 2 and 5 back to the carbonyl. And then the eighth step converts the thioacetal, which was on carbon 1, back to the carbonyl. Yeah.
Okay. This is not in this question, but like
Mhm.
if you have an aldehyde and you have drones, will it convert to carboxylic acid?
Yes, yes, it will.
Okay.
It will.
Okay.
Yeah.
Yeah.
Yeah. But if you have an aldehyde and react that with PCC, no reaction. Because
Okay.
the most oxidized thing that PCC can go to is aldehyde.
Do you think you can walk me through another problem from the worksheet?
Yeah, yeah. 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 Can you like share the screen so then we could walk through that as well?
Yeah. It's question V.
V. Oh, yeah. So let's think about this step by step. On the arrow, what is the reagent here that's going to react, right? Like whenever you see sodium Na, what charge does that come with? Whenever you see sodium or potassium, like Na or K.
Oh, that's positive.
Yeah, positive charge. Whatever is attached to that positive charge is always negative charge. So whatever is attached to Na or K is always a negative charge. So the hydrogen here has a negative charge. That's a hydride ion with a negative charge on the hydrogen. This hydride ion here is a very strong base, right?
Okay.
If that's a very strong base, we're going to look for the most acidic hydrogen. What hydrogen here do you think is the most acidic in the reactant molecule?
Probably one of the alpha hydrogens.
Right, so those are relatively acidic because it could like do resonance as we deprotonate it and give that carbon a negative charge, right?
Mm-hmm.
But in this case, the more acidic hydrogen here is going to be the hydrogen on the most electronegative atom, oxygen. So the more acidic hydrogen here is actually that oxygen hydrogen right there.
Oh, okay.
Right. The alpha hydrogens are still relatively acidic, but not as acidic as the alcohol hydrogen.
Okay.
Right. So the hydride minus here is going to attack that alcohol hydrogen and then give that oxygen a negative charge, which is our nucleophile. Our electrophile here is going to be this carbonyl carbon right there. What is the name of the reaction? What type of reaction is it if we have a nucleophile on the same molecule as an electrophile?
Intermolecular.
Yep, intermolecular, right. Where this nucleophile here will attack the electrophile or attack itself, pop the bond onto the oxygen to create a 1, 2, 3, 4, 5, 6-membered ring. Right. Where the 6-membered ring that we're gonna draw is not this here, right? Because you notice how the first atom I labeled is not a carbon,
Mm-hmm.
it's an oxygen. So the 6-membered ring that I have to draw has to include that oxygen in the ring as well. Where that oxygen is number 1, and then let's say this is 2, 3, 4, 5, 6. At carbon 4, we have the ethyl group, so I'm gonna include that ethyl group right there. At carbon 6, we used that with double bond O, but that got popped up to become a single bond O minus. And there's something else on carbon 6, which is that isopropyl group there, right? These are the substituents here. Ethyl group on carbon 4, isopropyl group on carbon 6, like that, right? And then
Mm-hmm.
that is missing like there should be an H plus workup step here somewhere. Like assume H plus workup from H2O plus or H2SO4.
Okay.
Right. Where that's just gonna protonate the O minus to create this final structure here. Right. And then what kind of structure did we just form when we have a carbon attached to an OH and an OR?
I forgot the name.
It's
It's
okay, see.
like, wait, what is it?
Hemiacetal.
Hemias.
Yeah. Do you know the name of the one that has two ORs on the same carbon?
Is that just acetal?
Yeah, that's just the acetal,
There we
right?
go.
Hemiacetal is half OR, half OH. Acetal is full ORs, two ORs.
Okay.
Uh-huh. And
Um,
cyclic hemiacetals are stable to exist. Like in this case, it's a cyclic one, so it's stable to exist. But if it was an intermolecular reaction, then that's unstable.
okay.
Uh-huh.
And then when we're talking about acidity,
Mm.
is an alpha hydrogen more acidic than a hydrogen just like on an alkene or an alkyne? Like if we're
Uh,
ranking acidity?
yeah. So you're saying if you are trying to rank, let's say, this hydrogen compared to this hydrogen right here.
Yeah.
I'm gonna check the pKa values for that really quick. Let's see. That's a good question though. Let's see. Okay. So to determine which one is more stable, look at the conjugate base, which is going to be this right here. After we, let's say, deprotonate it, we get a negative charge on whatever that hydrogen was attached to, like that. We look at the one what is more stable. This negative charge here is more stable because it could do resonance, right? Which makes this more acidic because the conjugate base is more stable.
Oh, okay.
But that's not always the case because if we look at the example we did here with the problem of not that one, V, right? We saw that the conjugate base of the O minus cannot do resonance, but the conjugate bases of the alpha carbons can do resonance. Right. So it just depends. The reason why like this one negative charge here is more stable on the oxygen is because oxygen is a more electronegative atom than the carbon, right?
Yeah.
But if you look at this example here, the negative charges are on carbon, like they're both carbons, like they're the same electronegativity, so it doesn't matter in that case.
Oh, okay, that makes
Right.
sense.
But if you have a more electronegative atom like oxygen, sulfur, nitrogen, then that would be the more acidic hydrogen, the one that on the more electronegative atom.
Oh, okay. Thank you.
Yeah, no problem. Those were good questions. Those are good questions.
Thank you.
Oh, Brian,
Yeah.
if we want to do the cyclic acetal, does it convert both aldehyde and ketone into cyclic acetal?
Yes,
Okay.
it will if you have excess of the diol, like excess of the reagent, right? But if you put one EQ on the arrow or you see one EQ, which one do you think is going to become the cyclic acetal first?
Aldehyde.
Yeah, aldehyde. So if you have one EQ, aldehyde goes first, and then the second EQ does the ketone.
So if you don't want to like, if you have like multiple carbonyls on the molecule and you don't want to touch some of it, do you just use the HS, CH2, CH2SH?
Yeah, that one will select for the aldehyde over the ketone.
Only aldehyde, or it could also happen on ketones?
If there's excess, it could happen on ketones as well. But the problems I've seen, it only assumes one EQ and it only reacts with the aldehyde, like the problems I've seen with the HS,
Okay.
right? But it can react with the ketone if it's excess amount, like a lot of them. But just assume one EQ because I've seen one EQ on the problems.
Wait, let me show you something.
Uh-huh.
I'm just a little bit confused about like, couldn't you like for the first step do like one EQ of
The cyclic acetal.
yeah.
Yeah, you could have done that as well. That could have worked as well. One EQ of the oxygen version instead. That would only react with the aldehyde if you put one EQ.
Okay.
Uh-huh.
But like,
Right.
would that still be able to get you to the final product?
Yes, but then if you do the first step as the alcohol, right? Like the one with the oxygen instead, I mean, right?
Yeah.
The second step you do cannot be cannot be the one with the alcohol. They have to be different. So you notice how like at that third structure there are different protecting groups.
Yeah.
The reason why we want different protecting groups is because the reagents needed to deprotect each one is different. Like the reagent needed to deprotect the thioacetal, the one with the sulfur, has mercury, chloride, calcium carbonate, CH3CN, and water, right? But the reagent needed to deprotect the cyclic acetal back to the carbonyl is just water, acid, and heat, right?
Okay.
So if you use the first step as the alcohol one, then the second one has to be the sulfur one. And then the third step one has to be the water, acid, and heat because we want to open up the aldehyde one. Because the aldehyde one is the one that will get reduced by the LiAH4 to alcohol. Right? And then if the other one is a thioacetal, you don't use H plus H2O and heat, you use HgCl2 CaCO3, CH3CN, and water.
So it doesn't matter like what protection group you use in each. It just needs to be different, right?
Yeah, it just needs to be different, right?
Okay.
And then make sure to, when you deprotect it, the reagents are different as well, because those are different to deprotect each different one.
Okay. Thank you.
Yeah, no problem. Wait, that's good for synthesis type problems.
Yeah.
All right, Brian, I'm gonna head out. Thank you so much for your help.
Yeah, no problem, my friend. I'll see you. Have you been going to like my content review sessions? Like, I think I seen your name like somewhere before. Like your name looks familiar.
Yeah, I used to go, but then I got lazy and
Oh yeah, you've
I
been just
stopped
like watching the
going.
recordings, videos,
But I
and stuff
watched
like
the
that.
recordings, yeah.
Yeah, that's good. That's good.
But yeah, thank you so much.
No problem. Oh,
Have a
when are you
good one.
checking when you can see? Like summer or fall?
Yeah, I'm gonna do summer.
Summer. I see. Okay. Sounds good. Sounds good. I'll see you,
Yeah,
my friend.
so have a good one.
Yeah.
I'm still like a little bit confused when you can attack the carbonyl, like the C on the carbonyl, because does that only happen with organometallics
Organometallic and reducing agents.
and reducing agents?
Yep, and reducing agents, right? Like LiLH4 or NABH4. Those can react with the carbonyl carbon as well.
And all the other reactions reacts with the alpha hydrogen?
Beta hydrogen.
Oh, beta hydrogen?
Yeah, beta hydrogen of the enone. Right? The furthest carbon away from the alkene, from the carbonyl.
Oh, then is it only for the aldol condensation when you react with the alpha hydrogen?
Um, well, Aldol, Michael, and Robinson, they all use the alpha carbon as a nucleophile. All of them use the alpha carbon as a nucleophile.
Yeah.
Right? But for the Aldol reaction, that's the only one where the electrophile is the carbonyl carbon of an aldehyde or ketone. Right. For Michael addition, the electrophile is not a aldehyde or ketone. It's an enone. Right. I'll show you that. Where for Michael addition, the nucleophile is the same. It's gonna be the alpha carbon, but the electrophile is gonna be an enone, something like that.
Okay.
Right. Where the beta carbon of the enone here, alpha beta, is the electrophile. Right. And then for Michael addition, we always form a 1,5 dicarbonyl. Right. Are you familiar with that reaction?
Not really.
All
I
right,
think
so let's
you
go.
went over this in today's lecture.
Oh, he did? The Michael addition one?
Yeah.
Yeah, so the first thing is that this will always happen in basic conditions because we want to form the enolate ion where the alpha carbon is the nucleophile. Right? I'm gonna draw out like this. Um, this O minus here is not the nucleophile. The nucleophile is this alpha carbon right here. When we reform that double bond between the carbon and oxygen right there, that alpha carbon is gonna attack the electrophilic carbon right there. And then shift the double bond there and then pop the double bond to the O minus. This is the electrophile instead of the carbonyl carbon because you know how I drew the resin structure earlier? There's a full positive charge on that carbon, but no positive charge on this carbon here.
Yeah.
Right? Like it's this resin structure right here. Well, I think I drew it on his screen, but when we do the resin structure, this get full positive charge on that carbon. And there's no full positive charge on that carbon right there, which is why soft nucleophiles like the enolate here will attack that beta carbon right there. Right. So when we make a new bond between the star and dot carbon, this is what we get. Star, dot, new bond between the star and dot. The dot is attached to a methyl group, that bond, double bond, O minus dot. And then the last step here is to tautomerize this enolate by protonating the alpha carbon using water. That would give us our 1,5-dicarbonyl. Oh, wait. No more double bond, alkene. We have a carbonyl. Right, or this is 1, 2, 3, 4, 5. 1,5-dicarbonyl.
Can you scroll up a little bit?
Yeah.
Okay.
The nucleophile for Michael is the same as the nucleophile for Aldol. Alpha carbon of enolate ion. The electrophile for Michael is the beta carbon of enone. The product is a 1,5-dicarbonyl. And this also happens in basic conditions. We need basic conditions to deprotonate the alpha carbon to generate the enolate ion.
Okay.
Right, which is the step here, the first step.
Is Michael addition always gonna be 1,5?
Always 1,5 for Michael addition.
And Alda is always 1,3?
Oh, right. 1,3 between well, not two carbonyls, because for aldol, we create a carbonyl, and then 1,3 to that is an alcohol, not a carbonyl.
Oh, okay.
Right. And that's condensation, but you most likely won't end there. You most likely will get rid of that alcohol and put a double bond between the alpha and beta carbon as your final answer.
Are the 1, 2, and 1, 4 additions still like Aldo, or are there different reaction?
The 1, 2, 1, 4 addition is the reactions with an enone, a alpha beta unsaturated carbonyl. That's different than aldol.
Oh, okay.
Right, because the electrophile for that is the enone, the beta carbon of the enone. The electrophile for the aldol is the aldehyde or ketone carbon.
Okay.
Yeah.
That makes sense. Yeah, thank you.
Yeah, no problem. It's a lot.
Yeah.
Yeah, I remember last quarter, when we're Anakin, that guy at the end of like one of the sessions, he was asking me these kind of questions on the chalkboard, and we did it, and then like you stayed afterwards, and then you're like, oh, this looks confusing. This is the part here.
Okay.
Yeah.
I
Yeah.
think this is even more difficult than
118A.
Dios are older. I
Oh,
thought
this order?
that Dios are was the most difficult part.
No. This is the most difficult part. The
Okay.
Robinson run. Robinson combines Michael and intermolecular aldol reactions together. Robinson.
Okay.
Yeah.
It's just really confusing with all the Enolate, Enon, and stuff.
You mean acetal, hemiacetal,
Yeah.
cyanohydrin, all those things, yeah. Dang. It's a lot of material for the last 2 weeks.
Yeah. Are you doing like a review session tomorrow?
Yes. Tomorrow I don't have anything planned. I'm just gonna go answer questions, do practice for Mascal's, and do practice from Helix, necessary and stuff like that. And go over also um Mascal's lecture, like the stuff that I missed during my content review and previous sessions.
Okay, that makes sense.
Yeah.
Yeah. Thank you.
No problem, Zinyan.
I'll see you tomorrow.
Yeah, see you tomorrow. Oh my gosh.
Yeah, I just like literally just like close all the lights, and then I just I close all the lights, and I'm just like lying on my bed ready to sleep.
Ready to sleep? You're getting ready to sleep? Were you just like patiently waiting until the end of the office hours to end?
Yeah.
Dang, what time have you been waking up recently these days?
Honestly, I went to sleep, but then like for some reason I keep getting waking up at 5 because my freaking window is like next to my bed, and like it just shines on my face, and I just wake up automatically.
Oh dang, that and then you've been sleeping at 10, so that's like around 7 hours of sleep. That's pretty
Well, it's like
good.
5 hours, and it's like it sucks, so I'm just gonna try to sleep at earlier.
Oh, because you were sleeping at midnight those times.
Yeah.
Oh my gosh. Yeah.
Also,
Dang.
I signed up for like a swimming pool membership where like I just like um let's see, it's just a season pass, so like I get to go there like for like the whole time is like through June, July, and all the August for $75
Oh,
because
wow.
yeah
Yeah, but that's like
because
the whole summer.
they used to charge like $5 per
Mhm.
person, and basically if you to go for 20 days, that'd be $100.
Dang, that's good. That's a good deal, actually.
Yeah.
Yeah. Oh, that was a good talk, good session, good catch up. I'll hope you get some rest and sleep tight.
Yeah.
Yeah.
I'll talk to you more about AP Chem after your finals end, I guess.
Yeah, it's gonna end next week. Yeah.
Yep.
Yeah. Mhm.
I have the potential to like finish all my summer school by next week.
Oh, really? Like you checked all the assignments and stuff like that already? And
Ye-
the readings and stuff?
Yeah, it's not really reading. It's just
Uh,
all just yeah, but that's just technology.
yeah.
It's still I still have summer reading for my AP Chem, my AP Lang class, but
Oh, like the summer homework, huh? Before that class starts?
yeah,
Oh my gosh, yeah. Dang. And then when we talk about AP Chem, I'm probably gonna have to like learn it with you like as we go because like I forgot a lot of things about AP Chem. I haven't been reviewing because like I've been like tutoring a lot for OChem, but we'll learn it
yeah,
together.
yeah. Thank you.
Yeah, no problem, Brian.
Hmm.
Yeah. Good night.